Welcome to the introduction of a series of lectures covering microsystems science for advanced diploma. In this first lecture, we will cover the introduction into embedded systems, applications of IoT, development platforms that we'll be using, C code, as well as how to implement algorithms. So the fourth industrial revolution that we live in brings about with it increasingly many applications for computer systems which are applied in controlling and sensing. Now, these applications rely on what are called embedded systems. Embedded systems are basically computing systems which are normally hidden from view, whose primary function of the computing device would not be computational, but that of implementing control. Now, at the heart of these microcontroller systems, at the heart of these embedded systems, we have the computing device being mainly microcontrollers. And microcontrollers have multiple components or subcomponents, as indicated in the diagram. And these subcomponents can be the transceiver, communication transceiver. It can be analog to digital converters, some memory, which includes RAM as well as ROM, and you can have as well as timers, as well as digital input-output interfaces. At the core of this microcontrollers is the processing unit, the central processing unit core. Some of these microcontrollers can have multiple cores, but all of these work together to create a microcontroller. An IoT application, or IoT, in this case, it's an increasing way of deploying embedded systems. So most of the embedded systems currently now are being deployed in the context of IoT, which is why it is our interest in this particular module to explore the use of embedded systems within the IoT. And IoT, which simply means Internet of Things, provides internet connectivity to things being physical objects. And the main reason behind this application is that we want to enable these things, these physical objects, to be smarter by connecting them to the internet. Applications of IoT range from transportation, healthcare, energy management, and the likes. There are many applications in this case. Now, for example, if we can consider a smart building application as an application of IoT, which will have the embedded systems. So in this case, a smart building application would have an aim of remotely monitoring and controlling appliances for user comfort as well as for the purpose of energy efficiency. Now, in this case, each appliance, these are the appliances: the geyser, the washing machine, battery pack, light bulbs. All of these are called things, and each of these would be connected to its own embedded system. So each of these would be connected to an embedded system, and the embedded systems in turn are networked. They are networked in order for them to be able to coordinate. And the control of these embedded systems, in fact, the control of these things through the embedded systems happens remotely on a remote server, which would be in the cloud, and this can be effected via a remote terminal. So all of these appliances, embedded systems, the network, local network within the building, as well as the internet connection, they all work together to create an IoT system for a smart building application. So these are the sort of build applications that we are looking at in this particular module. Now, there are multiple IO architectures that have been proposed, and there's no consensus on one particular architecture. But for our context, we will take a very simple architecture of an IoT system, which is composed of the 3 layers. On top, the application tier; in the middle, the communication tier; at the bottom, the perception and control tier. And in this case, the perception and control tier is made up of sensors and actuators, which are housed in these embedded systems, and they are used to digitize and transfer data to the communication layer. The communication infrastructure layer uses actually secure and efficient transportation of data and control commands in order to facilitate the control of the things at the bottom. And in this case, the communication tier can include both the local communication within the place of implementation, the building, for example, and also the communication can also between servers, between the local servers and remote servers via the internet. So the communication infrastructure tier simply contains all of that, both aspects, the long range, both the short range and the long range communication. The application layer provides services to the client. So the application layer is simply a software layer which implements the services that the client will require. And in this case, as in the case that has passed, the services would have been, in the case of a smart building, to make the house comfortable. So then this application layer in IoT applications would be implemented on a remote cloud server. Now, the series of lectures that you are about to receive, it's mainly focused on providing knowledge and background for the design of such embedded systems within the context of IoT. For the purposes of exercises in this module, we will rely on the use of 2 microcontrollers. The first one is the Node MCU, or the ESP8266 microcontroller. And this microcontroller, it's a low-cost Wi-Fi microcontroller developed by Esprit Systems with an internal TCP/IP protocol support. It features a 32-bit CPU and as well as Wi-Fi capabilities, a single analog to digital converter with 1 port. In this case, the ADC would be located here, which is ADC0, and then it features multiple serial communications protocols, SPI, I2C, as well as UART. And in terms of memory, it has SRAM as well as 4 megabytes of flash. And then the way it's programmed is via a bridge controller, which connects through the USB cable. That's how it's being controlled. And it features also on the board a low drop output regulator, low drop output voltage regulator, which converts the incoming 5 volts from the USB port into 3.3 volts, which runs the microprocessor. And it has an internal LED pin, an onboard LED, which can be controlled without connecting anything. And it also has a reset and flash buttons, as can be seen from this diagram or layout. It can come in different layouts. It does come in multiple layouts, which sometimes have fewer or pins as many as the ones shown here. The second important microcontroller platform that we'll use is the Arduino Uno. The main reason being that the simulation CAD software that will be used can readily be able to use Arduino. So Arduino features a less powerful 80 mega 328P microcontroller. It's widely used and there's lots of examples online, which makes it easier to work with. And it will primarily use it for simulation within Proteus software. The features of this Arduino board is that it is able to connect with Wi-Fi using the correct library and the correct attached hardware. By itself, it does not have the Wi-Fi like the Node MCU by default. And then it has 6 10-bit ADC pins instead of the single one that the Node MCU has. And it supports the SPI and I2C serial communication protocol. So we'll use this basically to verify our simulations. So it has many other features like the PWM, which is the analog output. It's able to handle interrupts and so on and so forth. So we'll learn this as we go on through the course. Now, the development of the embedded systems for this course will be done in Arduino, and we will use Arduino IDE Studio, which has the look as shown here, to develop our code. The good thing about this IDE, as well as the language of Arduino, is that it has multiple libraries which are already ready to be used for 8266, and it has many examples that you can try to learn the language. Now, the structure of the program, as far as Arduino is concerned, we will have two main loops or two main functions. The first function in this case is called the setup loop, and the second function, the second function will be the loop. And the code runs such that the setup function runs initially before any other code can run, and this mainly runs once after the microcontroller has just been reset. And then what then happens is, after the setup runs, then it will keep on executing line by line all of the instructions within the loop function. So a simple Arduino program with nothing will look like this. So you'll have a setup function which runs once at the beginning, and a loop function which runs for eternity. Now, Arduino language it's simply C++, and if you are aware of C++, as all of you are, you will see that it will have many inbuilt functions actually, which will be useful for us to program microcontrollers very quickly, such as, you see this one, which is called pin mode. This will be used to set the mode of a pin, if the pin being the input or output pin, or a leg of that microcontroller, to know how to interface it. And then it could have, for example, a function which is already written into that would be digital read. This would be equivalent to reading what the input is at the particular pin. For an analog pin, you can have analog read, and Arduino will immediately know what that you want to read, the value of the ADC linked to that particular input pin.